All right, good morning, everybody. So in the last lecture, we were talking about substitutability. So basically in substitutability, you have to make sure when you're implementing your classes that the subclass behavior satisfies all of the requirements of the superclass. Right, so in last lecture, we saw what happens when you have a method. You override a method. The method has some restrictions on the parameter values. And so we saw what happens when you subclass a method and your subclass doesn't have compatible constraints on the parameter values. Right? So something similar happens with the return values. So every method promises to return, every method that returns a value promises something about the value that is returned. So if a subclass overrides that method, it has to satisfy the same requirements that the superclass method satisfies. Right? So remember the width method and the height method, these both return a value that's between 1 and 100. Right? So that's their promise. So whatever your subclass does, if it overrides width or height, it must also return a value that's between 1 and 100. So for example, someone uses your shape class to create a method that changes the size of the shape so that the width of the shape becomes 1. Right? So in other words, it scales the shape uniformly so that the width becomes 1. Right? You can write this method as long as the height of the shape is bigger than the width. Right? And if the width of the shape is not 0. Right? So for example, you can write the following. This is slightly different than what the slides that are online. So I found this mistake a couple of days ago and made a change, but I didn't upload the change to OnQ. So as long as the height of the shape is greater than or equal to the width, right, then all you have to do is take the height of the shape and divide it by the width of the shape. Right? You're going to do the same thing to the width, but that's just going to make the width equal to 1. Right? And then you're going to call set dimensions with the width and height. Right? And that should pass every test that you can write. Right? So the width is 1, so that's a valid width. Right? If the height is greater than the width, then the height is greater than or equal to 1. Right? And so the height also satisfies the constraints of set dimensions. So this method should always work. Right? It should always either change the dimensions of the shape so that the width becomes 1, or it should do nothing to the shape. Right? So you can write every possible unit test for that method, and it will pass. Right? That method is correct as far as the shape class is concerned. Right? So suppose someone comes along and makes a vertical line class. Right? So a vertical line has a width of 0. Right? Or at least they define the width to be 0. Right? Now that's bad for 2 reasons. Right? So you now have broken one of the class invariants of shape. Right? Shape says every shape has a width of at least equal to 1. Causes a second problem now. So when you return the width of the vertical line, it's 0, and that's not between 1 and 100. Right? So it's easy to do, right? It's easy to make this class. You just create a constructor, call the superclass constructor, right? Set the width to 0, because that's the width of a vertical line. Right? What does it return? What does the method width return? Well, it returns 0, because that's the width of a vertical line. Right? What happens now back here when you pass a vertical line into the method? Right? Well, you divide the height by 0. So now the height becomes infinite. And when you call set dimensions, this throws an exception. Right? And so what's happened is by subclassing shape incorrectly, you've broken someone else's method that is supposed to be correct. Right? Or is provably correct at least according to the contract of shape. Okay, so notice what happens here, right? The language lets you do this. The compiler can't check that that your code is correct, right? It can only check that it's valid Java, right? It can't check that that when you overrode width, you actually obeyed or actually respected the contracts that were in the method that you just overrode. So the onus is on the programmer to make sure that when they override a method, that whatever return value the superclass says, or whatever the superclass says about the return value, the overridden method must respect what the superclass says. Right? So that's the return value. Now, it doesn't mean that you have to return the same value that the superclass returns, right? All it means is that you have to pay attention to what the contract for the superclass method says it returns, right? So you can return a different value from the class that you are inheriting from, right? So remember there's this area upper bound method, and the area upper bound method in shape says it returns an upper bound of the area, right? But for a triangle, you can compute the exact area of a triangle trivially, right? So the exact area of the triangle is just 1/2 the width times the height. So that value satisfies the contract of the superclass, right? The true area of a triangle is an upper bound on the area of the triangle, right? And so you can change the value of the method, you can change the value that a method returns as long as you still satisfy the superclass contract. All right, so one more thing. So what happens if you have a method that changes a shape, right? So in other words, you have a mutator method. So if a superclass method promises to change the state of an object in a particular way, then the subclass that overrides that method must ensure the overridden method changes the state of the object in a way that satisfies the superclass promises. Right? So back to square. Now remember, square is this shape where we've inherited from rectangle, incorrectly inherited from rectangle, and our current implementation of set dimensions forces the width and height to be the same, right? If they aren't, then it throws an exception. We already saw that's a bad idea, right? So as the implementer of square, you might say, well, I can fix this problem, right? So I'm going to fix the problem like this, right? So in set dimensions, I'm just going to ignore the height. So when I set the size of the square, I'm just going to use the width that's passed in, right? And I'm just going to ignore whatever value was passed in for the height. Right. Now the problem with that is that the superclass version of the method, right, the shaped version of the method says, when you call set dimensions, if the width and height are legal, then the width and height of the shape change to that width and that height. Right? So now you have a method that doesn't satisfy the superclass promise. Right? Why is this a problem? You can easily come up with a problem. You can easily come up with a situation where this becomes a problem. Right? So imagine someone looks at the shape class and they say, well, I'm going to write this method that forces the size of a shape to fit inside a certain other shape. Right? So I have some arbitrary shape. I'm going to fit it into a rectangle of a specified size. Right? If you ignore the height of the square, then that method may no longer work. Right? It may no longer fit the shape into that method that the person just wrote might not work for squares anymore. Right? So again, this fix to our set dimensions method doesn't work, right? So suppose you try to fix it again, right? So instead of trying to do something in set dimensions, right, we're just going to do nothing. So in other words, we're going to ignore both the width and the height. And instead, we're going to say, hey, look, if you want to change the size of this square, you ought to use set length. Right? This introduces a second problem, right? So now people who are using your hierarchy of shapes, right, they can't use the shape methods to work on squares if you want to change the size of a shape. Right? Now they have to know that there's this special set dimensions method. Right? Furthermore, they have to treat this as a special case in any method that decides it needs to change the size of a shape in a certain way. Right? Now they have to write code that says something like, if the shape is an instance of a square, call set length instead of calling set dimensions. Right? So that's no good. If you find yourself in a situation where you're writing code like that, so inside a method you're writing if your object is an instance of something, right, then you should probably stop and rethink what you're doing because something's probably gone wrong at some point. Right? It's fine for equals because that's the only way you can reasonably implement equals. Right? But generally you should avoid querying objects for their type. Right? You want to avoid that if you can. Again, you can come up with many situations where the fact that you're doing nothing in set dimensions causes a problem. Right? Okay, so that's all I want to say about inheritance for the time being. Does anybody have any questions about inheritance in general, when you would use it, et cetera, et cetera, et cetera? Yes?
For the square and rectangle example,
yeah.
How should square just be its own shape that doesn't inherit from rectangle at all?
Square doesn't fit into the shape hierarchy at all.
At all,
No, because the shape superclass says every shape has an independent width and height. Yeah. So there's no way you can actually, there's no good way that you can actually force it into that hierarchy. Good question. Okay, so there is, so I have one question for you. So we learned a little bit about abstract classes, right? And we also learned about interfaces. Right, so let me just flip all the way back to the beginning. Oops, let me flip all the way back to the beginning. How about we do it the easy way? Where is, oh, sorry. Oh, here we go. All right, so we have shape as an abstract class, right? So in an abstract class, you can't use the class directly to make an object, right? So nowhere have we tried to write new shape anywhere, right? And so the purpose of an abstract class is to serve as a superclass, and it declares all of the methods that are common to all shapes, right? But that looks a lot like an interface, right? So remember what an interface does. An interface says every object that implements this interface must have these methods, right? And so what's the difference between an interface and an abstract class? And so when would you use one or the other? The answer is actually on the slide, if you just read the slide. Yeah?
I could be wrong, but doesn't interface declare fields as well?
No, an interface does not declare any non-static fields.
Okay.
And that's basically the answer, right? So if you're in the situation where you want to specify both the methods and the information that every object has, then you can use an abstract class, right? If you're in a situation where you only need to specify what methods a class has, then you can use an interface, right? So an interface specifies behavior. Abstract class specifies both behavior and information, right? And that's the difference. That's the main difference. Okay, so we're done with part 3 of the course. So that's relationship between classes. Oh, there's Steam. Inheritance. So now we want to talk about part 4. So part 4 of the course is generics, but also data structures a little bit. And hopefully this sets you up for your data structures course in a nice way. Okay, so remember we implemented this stack class, right? So we have a stack of strings and we have a stack of ints, right? And both of these classes are separate, right? There's an int stack, there's a string stack, or just a plain old stack, I guess, or string stack class. Right, so remember, int stack looks like the following. It has an array, right? That stores the elements of the stack, right? Top index doesn't really matter, and we have push and pop, right? So push takes in an int to store in the stack. Pop returns an int that you get after popping the top of the stack. All right, now what happens if I want a stack of strings, right? And so if we didn't have generics in the language, one solution would be to create a separate class, right? So now you cook up your class called string stack, right? And then you start to implement your string stack class, right? And so you say, well, a stack of strings is basically like a stack of ints. So what if I just copy the code from int stack and see what happens? So copy the code from int stack, change the name of the class, right? Now I need an array of string because it's a stack of strings, right? So push has to change. Right? So it now takes in a string as an element, and pop returns a string when you pop the stack. Right? So that doesn't look too bad, right? The changes look pretty small. Right? And in fact, that is exactly the case. Right? If you go and look at the methods, you'll see again, there's almost no changes required to the class. Right? So we go inside and look at the pop method, only one line changes. Right? The element that comes out of the stack is now a string instead of an int. Right? Everything else, the code's all the same. Right? So the only thing that's changing here are these types. Right? And so it would be nice if I could just take, if we just could get the compiler to substitute string for int everywhere where we need to do so. Right? And if the compiler could do that for us, I mean, that would be pretty nice, right? We wouldn't have to do all of this manual work ourselves. Right? And this is exactly what Java generics are for. Right? They let you create a class or a type, right, where one of the parameters of the type is a type. Right? So in our stack class, right? We would like to make a stack where we could say what is the element type of the stack. Right? Okay, so the Java language doesn't actually work this way. Right? So in other words, the compiler doesn't actually make up a new class for you every time you make a stack of a different type. Right? You can manually do it, but the compiler doesn't do it for you. In a language, there is a language called C++, which you will eventually see, where this is in fact how they implement the generic types in C++. Right? The compiler does in fact do the substitution for you, and it does in fact produce a new class. Right? Java works a little bit different. So before they actually introduced generics into the language, right, people realized that this was a problem. And so they came up with a solution. Right? So the solution in Java is, instead of making a stack of strings or a stack of ints or a stack of dates, you just make a stack of object, because object can hold a reference to any type. Right? And so how do you do that? Well, if you use a list, it's easy. Right? You just make an array list of object. Right? So I'm calling this list object stack. Right? And you don't really have to make any changes to the class. Right? Push now takes an object as a parameter, and pop returns an object as its return type. All the other code stays the same. Right? And this works just great. So I can make a list object stack, and I can push a bunch of strings onto the stack, and it works just fine. There is a disadvantage, though. Right? So pop always returns an object reference, which is annoying. Right? Because if you make your stack of objects and you always push a bunch of strings onto the stack, right? You know when you pop the stack, you're always going to get back a string, right? But now our class is always returning an object reference. So now you have to cast the return type every time you call pop, which is super annoying, right? So here I'm going to make a stack of strings. I'm going to push some strings onto the stack, right? And now I'd like to pop the stack. So I can call pop, that's fine, but it returns a big O object. If I want to use the popped object to call to uppercase or some other string method, right, I have to cast the return type to string, right, which is annoying, right? I know as the user of the class, I'm only putting strings, right? Why do I have to cast the return type every time, right? So that's a little bit annoying, but you can work around it. There's a more serious problem, right? So the real problem is that if you're given a stack whose element type is object, you can put whatever you want onto the stack, right? So if you have a stack of strings, there's nothing stopping anybody else from pushing an int or a date or something else onto that stack, right? The compiler can't help you at all, right? Because as far as the compiler is concerned, all of these things are substitutable for object, so you can push them onto the stack, right? So for example, here's my stack of strings. I've got some strings, right? I can even push what looks like a primitive value onto the stack, right? Now remember what happens when you push 1 onto the stack, right? You don't get the int 1 on the stack, right? The compiler does some magic, right? It turns the 1 into an integer object, and then it pushes a reference to the integer object onto the stack. But it looks like you can push an int. You could push a new stack onto the stack if you wanted to. You can push a date onto the stack. You can push whatever you want onto the stack, right? They all work. And the fact that you can push whatever you want onto the stack means it's impossible to write a method that is type safe, right? So in other words, it's impossible to write a method using this stack where the method assumes, or where the method requires that the stack contain a certain element type, right? Because there's no guarantee that the stack that gets passed in actually contains only that element type. Any method that you write will compile cleanly, right? So you can build your program, you can run it and test it, right? But you won't know that there's a problem until someone actually makes a stack, passes in a stack that has the wrong element type, and now it fails when you run the program, right? So for example, I can create a class called sum, right? It has a static method called sum and clear, and it takes in a stack of integers, right? All this method does is it sums the elements in the stack, returns the sum back to the caller, and the stack that was passed in is now empty. Right, that's why it's called sum and clear, right? Sums and clears sums the elements of the stack and clears the stack. Right? It's easy to write. Right? You just create a variable called sum. While the stack is not empty, pop the stack. Right? Now remember, everything that gets popped off the stack is an object, so I have to cast it to integer to add it to the sum, right? And then return the sum, right? So that clears the stack, stores the sum in this variable sum, and away you go, right? Oh, sorry. Okay. So what happens when you call this method, right? And you pass in a stack of strings, right? Unfortunately, it works, right? Because that's a stack of objects. Right? And so if you pass in a stack that is not made up of all ints, or integers, sorry, this cast fails. Right? And it fails at runtime. It doesn't fail at compile time. Right? So the cast fails, and now you get an exception, and now your program crashes. Right? And so you don't want that to happen. Right? If you're writing this method, you really want to only let people call this method with a stack of integers. Right? And so Java generics lets you do that. So in Java, you can parameterize a class, interface, or method over types. That just means that you can use a type, one or more types, as variables that belong to the class. Right? So instead of making separate classes, int stack, string stack, date stack, et cetera, you write one class. Right? And now the class has a parameter that's a type. So that's what this angled brace notation is for in Java. Right? Stack integer means it's a stack of integer. Right? Stack string means it's a stack of strings. And stack date means it's a stack of dates. The compiler will ensure that the only thing you put into this stack is an integer. Right? The only thing you can put into the stack is a string, and the only thing you can put into that stack is a date. I guess, or a subclass of integer, or a subclass of string, or a subclass of date. Right? So in other words, the language guarantees that these types of classes are type safe. Right? So I can go back and write this method, and here I would just say stack, brace, integer inside. Right? And that guarantees that someone can only call the method with a stack of integer. Right? If they try to call it with something else, the compiler won't compile the program. So it's easy to make a generic class. Right? You just create a class, and then you put the angled braces in. Right? Then how many type parameters your class needs, you just list them here. Right? So some type parameter name here, comma, type parameter name, comma, and so on and so on and so forth. Right? So these type parameters here, they're any non-primitive type. Right? Anybody that uses your class will specify what they are. Right? So they might say string, double, integer here, for example. When you create the class, though, you don't put string, double, integer here. Right? You just put in some generic name for the types. Right? And so the recommendation for these generic names is that you use a single uppercase letter for the name. Right? So in other words, keep your type parameter names as short as possible. Right? If you have a collection of stuff, then the common name for the parameter is E for element. Right? If you have a map, then K and V are used. Right? So one type for the key, one type for the value. If your type has only numbers in it, you can use N to indicate that it's a numeric type. And in general, you can just use T for the generic type name. Okay, so let's cook up the simplest possible class that you can, the simplest possible generic class. Right, so in Java, you can method only returns a single value, right? Which is annoying, especially if you've learned Python, because in Python, you can return as many values as you like. Right? If you're writing a method like max, right, where you want to find the maximum element over a list or an array, it's nice to have both the maximum value and the location, or the index of the maximum value. Right? So you'd like to return two values from the method, but you can't. What you can do, though, is you can make up a class where you can make an object that can store two values, right? And so we can do this, if we want this to work for any max method, we can make this class generic, right? Like that, and that's it. There's your generic class that can hold two values, right? So that's called pair, it holds a value, one value of type T1 and a second value of type T2. Right? The field called first, right? Its type is T1. It's public, so somebody who makes an object can just use O.first, right? And second, its type is T2, and it's also public, so someone who makes an object can again just write O.second, right? And now you can get the first and second, or the two values from the pair. Right? You don't need a constructor because the compiler will make one for you, right? It'll set first and second to null, and that's it, right? That's all you need to use this class. So now I can write max, right? If I want to find the maximum element of a list of integer, right? And I also want the location of the maximum element, then I can return a pair, right? One of the values will be the maximum value. I think the first value is going to be the index of the maximum element. The second value will be the actual value of the maximum element. Right? So the result, you just make a pair object. That should be result. There's a mistake here. I still need to call a constructor, so I still need to do a new pair. And, it's generic, so we really should write new pair brace like that. Okay, so I make my result object to store the index and the maximum value. Right? I'm going to assume that the index of the maximum value is the first element in the list. Right? The maximum value will be the first element in the list. And now you just loop over the rest of the elements in the list. Right? Every time you find a larger element, you just set first to the index of the larger element. You set second to the actual value of that element. And then when you're done, you've got the maximum element and its index, right? You just return result. Whoever gets the pair back just writes, P.first and P.second to get the index and the maximum value. Right, so that's there's a very simple example of making a generic class. So can I turn the stack class into a generic class? And the answer is yes, it's easy to do. Right? So I'm going to start with the array-based stack. Right? So if I want to turn array-based stack into a generic class, I add the type parameter here. Right? So after the name of the class, angled brace, right? I need one type, the element type of the stack. So I'm going to use E. You could also use T here, that would be fine. Right? Now my array of elements, I want it to be an array of E, right? Whatever type the user makes the stack of, right? So if the user makes a stack of integer, this will be an array of integer, right? If the user makes a stack of dates, this will be an array of date, right? So that's what I want to write, right? Nothing else changes for the fields. Okay, so now in the constructor, I need to make that array. So I need to make a new array of type E. And so the way you would think you would do it is you'd write new E and then pass in the size and specify the size of the array. If you try to write that, the compiler flags that as an error. Right? So the compiler says, hey, I can't make an array of type E. Right? Now the reason the compiler can't make an array of type, maybe I shouldn't say it that way. So one of the reasons you might think that the compiler can't make an array of type E is because when in an array, the compiler needs to know how big an array, the amount of memory the array should occupy, right? If you don't know what object you're trying to store, you might think that you don't know how big an array you might need, right? So it's not super surprising that the compiler doesn't like this line here. That's not the actual reason in Java, but let's go with that for the time being. Okay, so it looks like you can't make a generic array in Java. So it looks like we're stuck, right? But you're not stuck, right? You just go back to our previous solution and you make an array of object instead, right? You might say, hey, if you're making an array of object, whenever you pop the stack, the caller has to cast the return type, but that's not true. You'll see how we solve that in just a second. So go back and change your generic type to object now. Right? Now, when you write new object, the compiler is perfectly happy with that. Right? Okay, so there's something you need to know about arrays in Java. So arrays are, when it comes to arrays and generics, they're not really compatible. So arrays in Java are said to be covariant. Right? All that means is that if you have an array of object, right, and you have an array of string, then it turns out that array is a subtype of the first. Right? So an array of string is a subclass of an array of object. Right? And so what does that mean? That means any array of reference type is a subclass of array of object. Right? Or a subtype, sorry, of the array of object. Okay, so what does that mean? So here's my array of object, right? My variable objs, right? What type of array can I store in this variable? Well, I can store any array of reference type in that variable, right? So if I make a new array of integers, I can store that in I can store a reference to that array in objs, right? So that does compile. All right, now, remember that in an array of object, every element is just a big O object, right? So objs0, that's the first element of the array, right? As far as the compiler is concerned, the type of objs0 is object. What can you store in an object? Well, you can store anything in an object. So I can store the string hello in objs0, right? Does it compile? Yes, the compiler lets that compile, right? Even though, right, the array that's actually stored in objs is an array of integer. So that does in fact compile, believe it or not. You can type it into Eclipse and see what happens, right? Does it run? The answer is no, right? Because when it runs, right, the virtual machine tries to store an array of string, tries to store a string, right, into this array. But the array is actually an array of integer, right? So at at runtime, the virtual machine discovers that you're trying to store a string in an integer reference, in an integer variable, sorry, right? And now it complains, right? So now it says I can't store a string in an integer, right? So that doesn't run cleanly. So the compiler lets it happen, but when you try to run the program, you run into a problem. Generics don't work this way. So generics are said to be invariant. If you have a list of object and a list of string, there's no relationship between these two classes. Right? The only relationship is that they're both lists. Right? So I can't take a list of string and substitute that for a list of object. Right? There's no inheritance relationship here. So now when you try to write the following, right, I have a list of object, right, and I try to store an array list of integer in that reference. Right? Now the compiler complains. Right? The compiler says, hey, you've got an array list of integer. That's not a list of object. Right? What is it? It's a list of integer. Right? But it's not a list of object. Right? So that does not compile cleanly. Right? And that's one of the reasons why using generics makes your code type safe. Right? It prevents you from doing stuff like this. Okay? But arrays don't. Right? Arrays will let you do that. Okay, so how do we implement push and pop? Well, there actually aren't many changes. So here's push, right? So the only line that changes in push is that, right? That's it, right? It's the exact same push method as before, except now our stack is always an array of object, right? It used to be an array of int. Now it's an array of object. That's it. Nothing else changes. What about pop? You only need one change. Here, the element type used to be int, right? And so the array also used to be an array of int, right? Now, our generic type is e, right? So our element type is going to be e, but remember the compiler still thinks that the stack, that the array has type big O object, right? And so now you have to tell the compiler, hey, the element type is actually e at this point in time, right? The compiler will warn you. It'll say, hey, this cast might be unsafe, right? But you know that the cast is in fact safe, right? Why do you know that the cast is safe? Because the only way that you can add an element to the stack is via push, right? What does push take in? Well, it always takes in an element of type E, right? So you know for a fact that the array only holds elements of type E. Therefore, you know as the programmer that this cast is safe, right? And now the rest of your code, and now that's it, you're done, right? So the only change we made was that, and that, right? And then the change in the constructor and the field, right? So it's not very hard in most cases to take an existing class and turn it into a generic type. You can do the same thing for the interface, right? So we had a stack interface where we had a stack of strings, right? If I want to make it into a stack, into a generic stack, it's easy, right? So there's our original stack interface, right? It took in a string, and when you pop, so push takes in a string, when you pop it returns a string, right? Now you just want to change that to E, change that to E, stick it in an E up here. That's it, you're done, right? So converting an interface is usually even easier than converting a class, right? There's just a few types that you have to change. All right, any questions so far? All right. Finally, right, we have this existing array stack class, right, which used to be an array of, our array stack class, what do we do? Here we go. Oh, wait, we already did it. So you have to make sure that your array stack class is in fact generic. Oh, sorry, it's generic, and now we want to say that it actually implements the stack interface, right? So you just write implements, and then stack, and then the generic type E, right? Here, that E and that E should match, right, in this case. Right? And away you go, that's it, you're done. You now have a generic interface. You've taken a non-generic class, converted it into a generic class, and all you had to do was make a few changes to the types. Okay, so let's try this for a different data structure. So let's try this for a queue. Right? If you don't know what a queue is, that's an example of a queue. Right? So it's just like lining up at a grocery store or anything else where you have to get into a line. Right? So there's a front of the queue, right? And there's a back of the queue. Right? You join, typically you get into line at the back, right? And you come out at the front. Right? Now, there are different types of queues, right, where you can jump the queue, right? So in other words, some VIP at a club might join the queue at the front, right? Or someone might get pulled out from the middle of the queue, either to get into the club early or to get kicked out, right? So there are other types of queues. Those are called priority queues. We're not going to look at priority queues. Okay, so there's only two operations on a queue. Right? You can add somebody to the queue, so that's called NQ. Right? You always add at the back. And then you can take somebody out of the queue, and that's called DQ. Right? And you always take the element out at the front. Right? Of course, you can't DQ an empty queue. That doesn't make any sense. Right? In an actual programming language, you would probably add some other operations. Right? It's nice to know how many elements are in the queue. Similarly, it's nice to know, is the queue empty or not? Some queues let you look at the first element but not take it out. So that's often called peek or front. Some queues let you look at the back element but not take it out. So that's usually called back. And then it might be useful to search a queue for an element, right? So it contains. In Java, you would probably implement toString and equals and hash code. Because it probably makes sense to compare two queues for equality. Okay, so if you're going to implement this, perhaps using an array or a list, right? How would you do this? So this is a picture of what happens, right? So starting with an empty queue, right? Front and back, there is no front and back, so we're just going to make them point at nothing. Okay, so when you NQ an element, right? The element appears, right? Front is going to point at the front element, and back is going to point at the back element, right? So in a queue of size 1, front and back are the same, right? If you enqueue another item, right, you add the item to the back of the list or to the back of the queue, and then you make sure that B, or back, points at the new back element, right? So enqueue the C like that, right? Enqueue the D like that, and then enqueue the E like that. Whoops, like that, right? Now, how does dequeue work? Okay, so for dequeue, the first element's going to come out, right? So you need to remember what the A is, right? And then you're going to remove that element, and then conceptually, right? So if you're going to try to mimic a line of people, right? All the elements shuffle forward 1 position. Right? So dequeue the second element, right? The B is going to come out, and then shuffle all the elements forward 1 position. Right? C comes out, the D comes out. I guess I should let this animate so that we reinforce that the elements are shuffling forward, right? And now the E comes out, and now you have an empty queue, right? If you try to dequeue the empty queue, typically an error occurs, right? So notice that a queue is a first in, first out data structure, right? The first element that gets into the queue is the first element that comes out. A stack is a last in, first out, right? The last element that you add to the stack is the first element that comes out. Right? Queues turn out to be very useful in algorithms when implementing other algorithms. They're also useful in real life, right? So queues, you run into queues every day, right? You go to the grocery store, you're in a queue of some kind, right? If you use a website and the website is even slightly busy, you end up in some sort of queue, right? So imagine if you're using, I don't know, Amazon or Google or something like that. There's probably millions of people also trying to use Amazon or Google, right? And so every time you try to make a request on the website, your request goes into a queue and then gets serviced somehow, right? So basically anything that needs to manage a finite resource, often they're managed using queues, right? So inside your computer, there's a bunch of queues, or your operating system, I suppose more properly, there's a bunch of queues, right? If you've got a printer, that's connected to your network, right? Then it's possible that many people are trying to access the printer at the same time, right? And so there's a printer queue, right? Inside your computer, you may have many processes running on your computer at the same time. They might all be trying to access the disk at the same time. So there's a disk queue, right? Similarly, if you have many processes running on your computer, they're all trying to access the CPU at the same time. So there's a CPU queue. Breadth first search is probably the most famous algorithm that uses a queue. There's a whole branch of mathematics / computing science / engineering called queuing theory that you can study. I don't know where you would take that course at Queen's. It's probably a grad course. Might be a 4th-year math course, but there is a whole branch of mathematics that deals with queuing. Right. Okay, so if we want to make a queue, turns out there's lots of different ways to make it. Well, there's not lots. There's several different ways to make a queue, right? Just like there's several different ways to make a stack, right? They're all going to have their own advantages and disadvantages. So it sort of makes sense to create an interface for queues. Then we can try making different implementations of queues, analyze what their advantages and disadvantages are, and then let them pick which queue they want to use depending on their problem. Right, so we're going to start by making it generic. Right? So the queue is parameterized by the element type that's in the queue. Right? It's useful to get the size of the queue or number of elements in the queue. We can implement isEmpty in the interface because we have a size method. Right? So we can make isEmpty a default method and give it an implementation. Right? So remember, if you have a default method and you want to implement, if you want to implement a method in an interface, you mark it as default, and the only methods that you can use are the methods that are also in the interface or in big O object. Right? So size is in the interface, so I can implement isEmpty. We have NQ and DQ. And we'll do front and back as well, right? So front returns the front element of the queue without removing it. Back returns the back element of the queue without removing it. Let's see. Okay, so when we implemented a stack, the first thing we did was try to do it with a list. So let's do the same thing with a queue. Right? So here is our queue implementation using a list. Right? We're going to use composition of a list. Right? Our list will be called queue. No argument constructor makes an empty queue. Right? Every constructor initializes its fields. Right? So for queue, the field queue, we make a new array list and assign that to this .queue. Right? What about the size? Well, the size of a queue is just the number of elements in its list. So we can just return this .queue.size. Right? You don't have to implement is empty because we got that from the interface. If for some reason you want to override that, you can, but it doesn't make sense in this case. Right? NQ. So NQ adds the element to the back of the queue. So for our purposes, we're just going to add the element to the back of our list. Right? So this .queue.add. Now what about DQ? Right? So, oh, sorry, we have throw if empty. So to DQ the queue, you can't DQ the queue if it's empty. So I'm going to call throw if empty. Right? That throws an exception if the queue is empty. Now, if you try to implement the queue using the pictures I showed you, right, you're going to remove the first element of the queue. Right? So that's going to be removing element 0 of the list. Right? Now the problem with this, when you remove the first element of a list, the list has to shuffle all the remaining elements one position forward in the list. Right? And so that takes n-1 operations. So your DQ using an array list has complexity big O(n), right? Which is not good. Right? If you have a lot of elements in the queue, that's an expensive operation, at least for a queue data structure. Right? There ought to be a way that we can do this in a faster, in not big O(n) time. Okay, front and back are easy because we have throw if empty. Right? So front, I'm just going to return the first element of the queue if it exists, or the first element of the list if it exists. Back, I'm just going to return the last element of the list if it exists. Right? I can get toString, no problem, right? Because our list has a toString method, right? So I don't have to do anything to implement toString. Equals is also easy, right? You do the usual equal stuff. So if this equals obj, if this get class if this get class equals obj get class, blah 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 blah, right? But then to check if they're equal, you just check if their lists are equal. So return this .queue equals other .queue. Right? So equals is easy too. So easy to implement if you use a list. But we have a slow DQ method. Right? And so in the next lecture, we're going to try to make that slow DQ method faster. Right? Hopefully we can get it to run in 01 time on average. Right? And we'll see how to do that in the next lecture. All right, have a good weekend. I will see you next week.